Continuing on our quest to find rules of derivatives, let's look at the derivatives of logarithmic functions. So if I have a log function and I want to know the derivative, I'm actually going to convert it to an exponential function because I do know the derivative of an exponential function. Derivative of a to the x is a to the x ln a. So let's go ahead and remember that if we have log to the base a of x equals, we call that y. If we write the equivalent exponential form, it is a to the y equals x. So I am now going to take this equivalent statement and I am going to differentiate both sides. So I'm going to use implicit differentiation. So I have a to the y and I want the derivative of a to the y is a to the y ln a, but then I've got the chain rule multiplied by the derivative of the exponent here because it's not x, it's y, which is a function of x, so that gives me dy dx, and that equals, now differentiating this side, the derivative of x is 1. So I can now solve this for the derivative of y with respect to x here, and that derivative is going to be 1 over a to the y ln a, but a to the y is x, so I could replace this with an x. And so the derivative of log to the base a of x is going to be 1 over x times the natural log of the base. Okay, well then if we wanted to know the derivative of the natural log, since the natural log is base e, I can use this formula and it's going to equal 1 over x times the natural log of the base, which is e, but we know that this ln and e undo each other, that just equals 1. So the derivative of the natural log is 1 over x. Derivative of log to any other base a is 1 over x ln a. Now that we have learned about the chain rule, anytime we learn a new rule of derivatives, and instead of having an x, if we have some function of x that we call u, we can still use the rule, but we just have to remember to apply the chain rule. So let's go ahead and apply that. We want the derivative of the natural log of 5x. So the derivative of ln u is 1 over u times the derivative of u. Oh, well that's still going to give us then 1 over x. Here I've got the derivative of a product, so I have y prime equals first times the derivative of the second. The derivative of the natural log of x is 1 over x plus the second, which is ln x, times the derivative of the first function, so that's just a 2. And so it looks like final answer, I have 2 plus 2 natural log of x for my derivative. Let's go ahead and look at one more example. This one is the ln of some stuff like ln u. The u in this particular case happens to be cosine x. And so the derivative of the ln of stuff is 1 over the stuff times the derivative of the stuff, and the derivative of cosine is negative sine x. So multiplying these, this would be negative sine x over cosine x then, which is just negative tangent of x. So seeing how this all fits, anytime we get a new rule, we've got to watch out for that chain rule. If it's not x but it is a function of x, we need to apply the chain rule. Now if it's not a natural log but it's a log, remember that we had this derivative of log to the base a of x equal 1 over x ln of a, and we know if it's not written that a log is base 10. So let's go ahead and apply this to find the derivative. And it is not x, it's some stuff here. Our u is 4 plus sine x. So the derivative is going to be 1 over the stuff, which is 4 plus sine x, multiplied by the natural log of the base, and the base is 10, and then multiplied by the derivative of the stuff, the u here. The derivative of 4 of course is 0, and the derivative of sine is cosine. So we have for our derivative cosine x over, I guess we'll just leave this as written. There's not really much we can do to simplify that. So there's our derivative. Another thing we're going to learn about then, and now that we know how to find the derivative of logs, is logarithmic differentiation. Because if I needed to find the derivative of this, This would be very involved using the rules we have, because essentially I have a quotient rule, but while using the quotient rule, when I need the derivative of the top, I have a product rule, but while applying the product rule, I have a power rule, chain rule, I have the radical, which is another power rule, chain rule, and this would be very complex, complicated to kind of keep straight. And so when we have quotients or products with different factors and quite involved, logarithmic differentiation can be useful. Before we learn what it is, we need to review the properties of logs that you learned in college algebra. Remember, when you have the log of a product, it can be expressed as the log to the base a of the first factor m plus log to the base a of that second factor n. If you have the log to the base a of a quotient, it can be expressed as log to the base a of m minus log to the base a of n. And the third property of logs is if you have a log raised to a power, that power can be multiplied as a factor out in front. So if you're rusty on these log properties, you will want to review those, because we are going to need to apply these various log properties in using logarithmic differentiation. So logarithmic differentiation, take the natural log of both sides of an equation and then use logarithm properties to simplify. Then we will do implicit differentiation with respect to x, and then we will solve the resulting equation for dy dx, or y prime, just the other notation, prime notation. So basically, let's see this in action for this particular function that we had been looking at. We could call f of x y, and basically we are going to take the natural log of both sides of an equation. Now we're going to use log properties to expand. We know that if we have the log of a quotient and then also of a product, we can take the log to each piece. So I'm going to do that for the two factors that were multiplied. I can take the log to each of those factors. I'm also going to express this radical as an exponent, because I'm going to use this log property in a minute. And then for the quotient, we're going to subtract. This would be the natural log of x squared plus 4. Now let's go ahead and use the third property of logs, and all of these powers can move out in front as factors. And so this is going to give me 4 natural log of x cubed minus 1 plus 1/2 natural log of 3x minus 1, and then minus natural log of x squared plus 4. Okay, so we have taken the log of both sides and we've used the log properties to expand. Now we're going to use implicit differentiation. The derivative of ln y, this is ln of some stuff, so it's 1 over the stuff times the derivative of the stuff, and we'll write this time as y prime instead of Leibniz notation. Okay, differentiating this, it's the ln of some stuff. The 4 is just a constant to be multiplied later, so we'll just put the 4 there. So it's going to be 1 over the stuff times the derivative of the stuff, and the derivative of x cubed minus 1 is 3x squared. Moving to the next term, we have the constant 1/2, and then the derivative of ln of some stuff is 1 over the stuff, so 1 over 3x minus 1 times the derivative of the stuff, which would be 3. And then we have minus, so the derivative of the natural log is 1 over this stuff, the u, multiplied by du, or the derivative of the stuff, which is 2x. We could now multiply both sides by y so that we can solve this for the derivative. And we actually know what y equals, because before this ln part we had y equals this. So we could substitute that circled stuff for the y, and we have, even though it's big and ugly, it was a lot easier to compute than a quotient rule, product rule with power rules and chain rules involved. So this would be 12x squared over x cubed minus 1 plus 3 over 2 times 3x minus 1 minus 2x over x squared plus 4, and then this would be multiplied by x cubed minus 1 to the 4th square root of 3x minus 1, and that is over x squared plus 4. Whew, we've got our derivative. One last thing is let's look at how log properties can help us. We know that taking the log of both sides and using the third log property enables us to solve exponential equations. Well, it's also going to enable us to find derivatives of some crazy things such as this. So the first thing I would do would be to take the log of both sides of this equation, and now I can apply the third property of logs and multiply this exponent out in front. So I have the natural log of y equals the square root of x times the natural log of x. I now am going to use implicit differentiation. The derivative of ln of some stuff is 1 over the stuff times the derivative of the stuff. Differentiating the right hand side, I have a product. So this is first times the derivative of the second. The derivative of ln x is 1 over x plus the second, which is ln x times the derivative of the first. Now I'm going to write this first function as x to the 1/2 because that's what the square root of x equals. And so differentiating is a power rule. Power out in front, decrease the power by 1. So this can be written as 1 over 2 square root of x, because we could move this to the denominator and then rewrite it in radical form. Now I can multiply both sides by y, and instead of writing a y here, y equals x to the square root of x. So I now have found the derivative of x to the square root of x.